should equal the final velocity. And it's a check. It's another way to check the final velocity. 9.8 times 5.5, and we get 53.9, or rounded off to 54 meters per second. So that's actually a good check. You can do things like this to check your answers, to see if in fact all of these, in other words, all of these equations should all agree with each other. If they don't, then something's wrong. Okay. I'm going to let's see. I'm going to do one more example question, just to give you an idea of one of the homework problems. This is the example problem on page 59. It's 2.9. The example problem at the bottom of page 59, and it's number 2.9. Okay, this is a problem that's a little bit more complicated. You draw a picture. Here's a cliff, and a person's right here. And this distance is 120 meters up. This distance is 120 meters. And here's the ground. And he throws a rock up with an initial velocity. The initial velocity is 8.7 meters per second. And the question is, what will be the velocity, what will be the final velocity when it comes back and it hits the ground? Okay. Well, how would you solve this problem? You know what the initial velocity is, you don't know what the final velocity is, but you do know what the distance is, the distance traveled. Okay? Well, think of an equation that doesn't have time with it. We have the final velocity squared equals the initial velocity squared plus 2ax. Okay? So in this case, this is a good problem to do because it introduces the idea of the signs are very important. This is a one-dimensional problem, but it's a one-dimensional problem in the vertical axis. Okay, so we can set a coordinate system here. So over here, I'm going to set a coordinate system, and this is instead of our x coordinate system being horizontal, our x coordinate system, let's say, is in the vertical dimension. And this is our 0 point. This is x. Our x dimension now is up and down. We go plus up, and we go minus down. And we're going to set at our 0 point, our 0 datum is right here at the top of the cliff, 120. So this distance down here at the bottom of the cliff is where x equals minus 120 meters. Okay, we could set it down here, but it's nice to set it your 0 point where the ball is initially, or rock is initially launched. Okay? So, now, which way is gravity acting? Gravity is acting down, so the acceleration is a minus 9.8 meters per second, because the acceleration is always acting in the negative direction, so we give it a negative sign. Okay? Whatever is positive, we give it a plus sign. Whatever is negative, we give it a negative sign. Now, the initial velocity is plus 8.7 meters per second. So it's going up, so we give it a plus sign. So what we want the final velocity. So the final velocity squared equals the initial velocity squared plus 2ax. Okay, so let's start plugging in, but be very careful with the signs. The initial velocity is 8.7 meters per second, all that squared, plus 2 times the acceleration is minus 9.8 meters per second squared times x. Notice, we don't want, here's one of the keys to this problem. The 0 point is here. If we said we want to solve in a plus x, that would mean we want to solve for where the velocity is up here. But now we want to solve for where the velocity is at minus 120. So it's minus 120 meters. So we take a calculator, and we say 8.7 squared equals 75 point, so I'm going to round this off to 76 plus, notice, here's another thing I should mention. Some of you will probably ask the question, where do we round off? And here's where I disagree a little bit with the author. What the author does is the author he multiplies these together, he rounds off, he multiplies these together, he rounds off, and then he rounds off at every step. I was trained not to do that. What I do is I actually, in fact, I would tend to argue, in fact, if you take 8.7 and square that, you get actually the full number is 75.69, and then I'm going to add to that this. What I do, and I would tell all my students, is you don't round off until you get to the final answer. Then you round off. The reason I would argue this, and the author of this book probably differs with me here, but actually I think I'm right here, is that when the equations are exact equations, this equation is an exact equation, there's no reason why, from a physical point of view, I need to take this quantity and round it off. In other words, so what we'd have to round off is the final solution to how many significant figures we have in the entire problem, which are 2. Okay? Hope that makes sense. 2 times 9.8 times 120, 2352. I'm going to add these together, plus 75.69, and I get 2427.69. That's the velocity squared. I now take the square root of that number. And here's where I round off to two significant figures. And I'm going to get 49 meters per second. If you look in the book, hope you can see that, 49 meters per second. If you look in the book, I think the author gets 50. I would argue that if you round off properly, it should be 49. It's just a minor difference. Doesn't really make that much difference. But, so notice that the final velocity here is 49 meters per second. Now, but notice this plus. Here's where another tricky part comes in. This could be, if this velocity were minus, then when you square this square minus number, you get a positive number. So notice that when you take the square root of this number, the square root can be a positive number or a negative number. We need to take the negative solution in this case because from a geometry point of view, we know that the velocity, the final velocity is going down. That gives us a minus number. Okay? So what I want to do is I want to, even though we've solved this problem, for clarification purposes, I want to explore this a little bit further. And hopefully this will actually make some sense. Okay, I'm going to take this and just erase it. But notice that our initial velocity going up was 8.7 meters per second. Our final velocity going down was, what was it, 40 minus 49 meters per second. Okay. Okay, what I want to do is to explore this just a little bit more to make sure you understand some of the mathematics of the physics that's actually going on. I'm going to draw the cliff again. Here's a cliff, and the initial velocity, you have the initial velocity going up, the rock comes up, and the rock actually goes up and down in a straight line, but just for clarification, I'm going to give it a little bit of curving here. The velocity goes up, and then it comes around, and then the final velocity is down here at, if this is 0, this is minus x equals minus 120 meters. Okay. Now let's explore the time part of this. We haven't done that so far, but notice at this point in time, right at the peak here, we can actually break this problem up into two parts. We can break it up into the part that it takes from a time point of view. We have T1 and then T2. T1 will be the time from where it gets, when it's initially launched up to the peak, and then T2 would be from the peak down to the very bottom. Okay? How do we solve for T1 and T2? Okay. We need to use an equation with time in it, right? Obviously, but think about the acceleration. We know that in this problem that the acceleration is a constant, and that's key. Notice that when you initially launch it, the acceleration is down. And that's actually what slows it up. But even when it gets to the very peak, the acceleration is down. When it gets here, the acceleration is always a constant minus 9.8 meters per second squared. That's very key to this problem. So let's start out. The acceleration is equal to the change in velocity over the change in time. So we have the final velocity minus the initial velocity, all divided by time. Now let's break this into two parts. the first part will be where we have an initial velocity and the final velocity at the very peak. The final velocity at the very peak is 0. When you throw something up at the very peak here, the initial, right at that instant, boom, the velocity right at the peak is 0, right there at 0, and then it starts to fall back down. Okay? So at the very peak, whenever you throw something up at the peak, right at that instant, the velocity is 0. So we can solve for that time. So we're going to say that we're going to solve for the time when the final velocity is 0 right at the peak. Okay? So the acceleration, and this will be the time to time number 1. I'll put T1. The time for T1. Okay, so T1 equals 0 minus the initial velocity, all divided by the acceleration, and I get minus the initial velocity is minus, well, the initial velocity is 8.7, but we put the minus number in front of it, minus 9.8 meters per second squared, and T1, therefore, is, notice that the minus signs cancel out. We get 8.7 divided by 9.8, and we get I'll round off to 0.89 seconds. Okay, so T1, I'm going to say T1 equals 0.89 seconds. Okay? All right, well, how do we solve for T2? We go back to this basic equation here, and we do the same thing. It's the final velocity minus the initial velocity, all divided by t, in this case T2. In this case, the initial velocity right at the peak, the initial velocity is 0. And the final velocity down here is a minus 49 meters per second. We saw for that before, okay? So in this case, the acceleration is the final velocity minus 49 meters per second minus 0. That's the initial velocity at the very peak, all divided by T2. T2 equals minus 49 meters per second, all divided by the minus 9.8 meters per second squared, and we get 49 divided by 9.8, and I get 5 seconds, exactly 5.0 seconds. So T2 equals 5.0 seconds. Okay? So I'm going to draw a picture that will help to explain this. Okay, I'm going to draw a velocity. On the x-axis, I'm going to put time. On the y-axis, I'm going to put velocity. So it will be a velocity times time versus time plot. All of these questions like this, you can always make these kinds of plots, and it should make sense. So on the y-axis, I'm going to put velocity. On the x-axis, I'm going to put time. Okay, and I'm just, for clarity, I'm going to erase a little bit around here. Okay. The initial velocity is at 8.7. I'm going to put that up here. 8.7, and this is in meters per second scale. This is meters per second. The final velocity is minus 49. So I'm going to say that's 0 and let's say minus 49, well, it's probably way, let's say it's way down here, minus 49. My scale's a little bit off, but notice here's the 0 point. So at t equals 0, the velocity is 8.7, excuse me, 8.7, and it's up. And the comes here. And this time, when we get to the very peak, is when we have 0 velocity. Remember, the velocity right here is 0 at the peak. That time is 0.89 seconds. So, but then notice that the velocity continues to go negative. This is supposed to be a straight line, and I will ensure that it is a straight line. So notice this is a straight line, and it at a total of, remember the total time here is 5.89, or about 5.9 seconds. So out at about 5.9 seconds, the velocity is a negative 49 meters per second. 49 meters per second, that's where it hits the ground. So notice that we can always draw these kinds of plots. This is the velocity times versus time. Here, this is the initial velocity. And now the velocity starts to decrease. And notice it decreases at a constant rate. And it goes through 0. Notice what's confusing to students at first, until you get used to it, is the fact that since this is a one-dimensional problem, the initial velocity, it goes up, acceleration pulls it down, and at the peak the velocity is 0. But notice that the acceleration, that is the slope from here to here, the slope is the acceleration of gravity, which is a constant. And that acceleration of gravity continues all the way from positive velocities to negative velocities, because this slope is a constant slope. That's the key to this problem. So we start off at positive velocities, and then we just slope right down through 0 down to negative velocities. In fact, it would keep on sloping down if the ground weren't there, and we'd go to larger and larger velocities, always at a constant slope of 9.8 meters per second squared. So I hope that this explains this problem a little bit better. Let me also go over one more item here, which we can also go over. Not only can we draw this curve here, but we can also draw time and distance. Let's see. Can you see this? Yes. This is distance. In fact, I'm going to draw it over here. I'm going to draw it. In fact, to make it clear, I'm just going to erase this. Here we go. Where this is time, and this is distance. Now notice that the distance, this is 0, this is plus distance, that goes up positive, and this is x. X positive goes up, x negative goes down, so x negative goes down. We can, and when we draw the y curve regarding to x, now remember, x equals the initial velocity times time plus 1/2 at squared. Notice that the acceleration is a negative number, so I'm going to write it this way, that it's 8.7 times t, I'm going to just fill in these numbers, a minus 1/2 9.8 t squared. I put the minus in here number because I want you to see that what we have here is a parabola, is a plus 8.7 t minus 9.8 divided by 2, 9.8 divided by 2 is 4.9 t squared. What we have actually here is a parabola in terms of t. So what that means is it comes up here and then it comes back down. So right at this point here is where we had the 0.89 seconds at the peak. At this peak here, we could even solve for the x peak, which if we wanted to, and down at a time of 5.2 seconds, the distance is way down here negative. It would be down here at negative 120 meters. So what we have here, we won't plot it out, but what we have here is actually a parabola in time. This is x, the distance vertically, up or down, versus time. So it's a parabola in time. We'll talk more about this later. Well, I hope this gives you a good overview of Chapter 1. We're going to do some problem solutions, and a next, you can jump from here to the solutions of some of the problems, and also be talking about the lab. Well, God bless you, and we'll talk with you later.